On to conservation of angular momentum and some informational practice. First of all, under what conditions is angular momentum conserved? Angular momentum is always conserved as long... linear momentum. Linear momentum is always conserved if there are no external forces acting on the system. Under what conditions is angular momentum conserved? Angular momentum is conserved as long as there's no torques acting on the system. Explain how rotational inertia and angular momentum concepts apply to the guy in the chair with weights who spins faster as he pulls his arms in. So remember, if you have the weights far apart, rotating about this axis right here, as it goes around and you bring the weights closer towards the center, R is now smaller. And if R is smaller, I equal kmr squared. So if R is smaller, that square means it has a big impact. If R is smaller, I is smaller. If I is smaller, then you have a constant angular momentum. If I gets smaller, what must happen to your angular velocity? It's got to get bigger. Conversely, if we increase the size of I, then that would mean your angular velocity would have to decrease. Because angular momentum is conserved in this instance because there is no external torques acting. Ice skater doing the triple axle, the same thing. We're bringing those atoms closer towards that pivot point, closer to the axis of rotation. Pulsars are stars in space that rotate very fast. It takes Earth 24 hours to rotate. One's about the sun and about 24 hours to rotate, and the sun about 26 days to rotate. But a pulsar takes 1 to 2 seconds to complete one rotation. Explain how this could happen. So pulsar is a star that was rotating once every 30 days or so. And it collapsed because it was no longer fusing. So there's no longer an outward pressure that was fighting gravity. So it collapsed, it condensed, all of the mass got smaller. So the diameter becomes about 20 miles wide. So if you decrease, again, if you decrease that R, and your angular momentum is conserved, I is going to become smaller. So your moment of inertia, your rotational inertia is tiny, and your angular velocity is gigantic. Suppose you are standing on a merry-go-round. The merry-go-round is freely rotating with no friction at its axis and no motor to keep the merry-go-round going. What will the merry-go-round do if you just stand there and do nothing? If you're just standing on the merry-go-round, there you are, and it's rotating like this. It's just going to keep going. Your omega is going to be the same. The same. I don't know if that the snuck its way in there or not. Name 2 things you can do that would cause the merry-go-round to go faster, just like in the above examples. If we decrease the distance from the axis of rotation, and in this case, it's going to be right there, right in the center. So what does that mean? Walk towards the center. That's going to lower your moment of inertia. That's going to increase your angular velocity because your angular momentum is conserved. Well, what about when your angular momentum is not conserved? You could have a friend exert an external torque to increase your angular momentum, right? You can have them push you around. When you're on the playground, just say, "Hey, friend, could use a bit of torque, if you don't mind. They'll know exactly what you're talking about. No big deal. They'll come over and they'll push you. And the out-of-the-box idea would be if your merry-go-round was rotating this way, you're going, and you start running in the opposite direction, the merry-go-round is going to have to compensate for that negative omega, that negative angular velocity that you are having. And it's going to do that by rotating faster. L equals I omega. And angular momentum is always conserved. So if this is staying the same, if our angular rotation is staying the same, but this becomes W minus W of U, so adding in that negative angular velocity is going to decrease our angular velocity term right here, which is then going to mean it's going to need to rotate faster right here. It's going to have to compensate for your angular velocity.